if you don't do any algebraic geometry, this is just some topological space. And here's another model. Set of all what I'll call V sub bullet. This is a full flag, right? Like this. So I look at the set of all full flags in an n-dimensional vector space, right? And the idea here is that G acts transitively, right, on the set of all flags. That just says if I have a list of vector spaces like this, I can map it to any other list by some linear transformation. That's a consequence of linear algebra. And B is the stabilizer, right, of a particular flag. Right, where the ith space is spanned by the first I standard basis vectors, right? This is B is the full stabilizer of this flag. It means every one of these spaces is invariant under B and not invariant under anything outside of B. And so we get a bijection, right, between the set of all flags and the set of all cosets just from group theory. And so this here is a so-called flag model. Right, and we can use these interchangeably, and we will. Okay, so this is the flag variety, right? And now we're going to look at some subvarieties of the flag variety, which are Hessenberg varieties. So the flag variety has been studied for quite some time. And there's a lot known about it. It arises all over the place in geometry and combinatorics and algebra. So these were first studied by Damari and Shaman. Then in a more general setting by Damari, Procesi, and Shaman. Right. And then by lots of other people, but we're going to be only concerned, there are more and more and more general definitions of Hessenberg varieties. We're going to be interested in the most restrictive definition, which is already given here. Right. So how does this go? Right, so it has to have something to do with this Hessenberg vector. Right, and so associated to a Hessenberg vector, is a Hessenberg space, which I'll call H sub m. This is a Hessenberg space. And it's, in fact, a subspace of, well, I'll write little gn, or I could write big mn. This is just all n by n matrices, right? And so this consists of all n by n matrices such that Aij is 0 if, let's see, I is bigger than mj. And of course, one example would illustrate this, right? So what we're really saying is we're cutting out some French style Young diagram from the lower left corner. So I have 2, 4, 5, 6, 6, 6, that's M, and HM looks like this. Well, I'm allowed anything I want in the first column down to the second row, and then I must have 4 zeros. Right. In the second column, I'm allowed anything I want. This is a 0 down to the fourth row, 0, 0. In the third column, I'm allowed anything I want down to the fifth row. And then in the last 3 columns, I'm allowed anything I want. So this is a Hessenberg space. It's very clearly a vector subspace of the space of all n by n matrices. Right, and this is just the definition we're going to take for a Hessenberg space. There are more general things you can say. And now let's take any n by n matrix. And these two ingredients, the Hessenberg vector and the n by n matrix, allow us to define a variety right? This Hessenberg variety. And I'll define it in both the coset and the flag model. So in the coset model, it's a set of all cosets such that G inverse SG, right, is in the Hessenberg space, right? And so one observation here is if you change the coset representative, you're not going to change, right, whether or not this conjugate of S is in the Hessenberg space. Because if I replace G by G times some element here, that means I'm first, if I conjugate by G times some X, where X is upper triangular, right? I'm first going to conjugate by G, and maybe that lives in this space. And if I take something living in this space and conjugate it by an upper triangular matrix, it's going to stay in this space. If you're used to adjoint action of a reductive group on its Lie algebra, this is clear. If you're not, this is just linear algebra in this setting. So this is well defined, is what I want to point out. And in the flag model, this is all the flags, right, with the property that SVJ is contained in VMJ, right, for all J. Okay. So this is the Hessenberg variety in both the coset model and the flag model, right? And let me convince you that this is right, that under the bijection that sends a coset to the flag obtained by applying the representative to the standard basis flag, in fact, corresponds in this way, right? That these are bijective to each other under the bijection from the flag model, sorry, from the coset model, the flag model. So let's check this out, right? G inverse SG is in this Hessenberg space. Well, it means that G inverse SG looks like this, which tells me something about where G inverse SG maps each standard basis vector, right? This is if and only if, right, G inverse SG applied to EJ, right, lives in the space spanned by the first MJ standard basis vectors, right? I have MJ non-zero entries down the jth column, right? And so this is if and only if, right, SG of EJ, right, is in G of this space here, right? And this is the same as what we want to say in the flag model, right? Right. So this is right. All right. So we either have this flag model, which for our purposes is going to be easier to work with for examples, or this coset model. Right, and so we can work with either of these. These are algebraic conditions, right? So this is a subvariety, right? This is cut out, right, from the flag variety by some polynomials. Okay. So far, so good. Okay. So these are many familiar varieties look like this. So let's first start with some examples. Well, there's the basic example, or the simplest example, which is that this basically means there are no conditions. If I apply S to the ith space, it's contained in the nth space, which is Cn. And so that there's no conditions here. Or, right, S is a scalar, lambda times the identity. Then when I just conjugate S by G, I get the same S back. And the condition on the Hessenberg vector that Mi is at least I means that the identity matrix is always in the Hessenberg space, right? So these conditions mean there's no restrictions at all. And SM is just the whole flag variety, right? That's one, right? There are some other familiar varieties. If M is 1, 2, up to N, and S is nilpotent. Probably shouldn't use S for a nilpotent matrix, but that's okay, right? Then this Hessenberg variety, right, is a Springer fiber. Springer fiber, these, right, are very carefully studied because they enable us to learn something about representations of symmetric groups or Weyl groups in general. If M is 2, 3, ... n, right, and S is nilpotent, then this thing here is a so-called Peterson variety, a regular nilpotent, sorry. S is, when it's in Jordan form, right, its only eigenvalue is 0, and it's got one Jordan block. S is a Jordan block of size n with eigenvalue 0. Then this is a Peterson variety. These are of interest in, again, study of flag varieties. There's a quantum cohomology that we're not going to get close to that. And this is the one I want to stick with this same vector. And now S is generic, which I'll say is regular semi-simple. Regular semi-simple means I'm diagonalizable with n distinct eigenvalues. All right, this is a generic element. I close my eyes, I pick an n by n matrix, it's diagonalizable with n distinct eigenvalues. So this is the typical case. I've got this m here. Then this is a toric variety. This is a theorem of Damari, Prachesi, and Shaman associated to the fan of Weyl chambers. Or if you like, the braid arrangement. Okay, so this is theorem of Damari, Prachesi, Shaman. And so, in fact, I would like to look at the smallest interesting case like this, and just so an example so we can see what these things are. Any questions?
Yes.
So I hope, go ahead.
Going back to the first one where you have 1 up to n, instead of S being nilpotent, what if it is regular semi-simple?
So then you're just looking, then you're going to have a point, right? I'm sorry, you're going to have n factorial points. Because what you're saying in that case, if your matrix is non-singular, it doesn't matter if you can choose any regular semi-simple one you want, so you assume it's non-singular, right? Then what you're saying is that you have a flag in which this non-singular matrix maps each space into itself and therefore stabilizes each space. And if I have a regular semi-simple element, right, then the only stable subspaces are things spanned by the eigenvectors, right, which are the standard basis vectors. So in that particular case, what you get are n factorial flags. You can kind of append the standard basis vectors in any way you want. So it's a discrete set of size n factorial.
Thank you.
That's a good question. The other thing I want to say is this is essentially, Teddy brought this up maybe in the first or second lecture, right? If m is 2, 3 up to n, right, then what is this matrix going to look like? It's going to be upper triangulus Hessenberg space along with the first subdiagonal, and then conjugating S so that S lives in HM is basically putting S into a Hessenberg form. And this is important in numerical linear algebra. And what Damari and Shaman were doing, we're using the topology with this particular M, the 2, 3, 4 up to n, right, that the topology of this Hessenberg space should control how quickly an algorithm can put a matrix into Hessenberg form. This is maybe reminiscent of, other combinatorial work, say of Björner, Lovas, and Yao on subspace arrangements, right, that control how quickly an algorithm can determine if, some number of entries in a given vector are all equal. So this idea is interesting and used. But that's not what we're going to talk about. I want to talk about a particular example now, namely where S is regular semi-simple M is 2, 3, 3. So this is Hessenberg, right? The Hessenberg space looks like this. Right, but I'm more interested in the flag model. And let's say S is diagonal, like this. One remark I want to make, I don't think I want to write it down, is that if you conjugate S, you do basically that means, right, if you fix M and conjugate S, then all you're going to do is translate the Hessenberg variety by the inverse of the conjugating element, so you can get an isomorphic Hessenberg variety. So if I want to take a generic element, I can just assume that it's diagonal, right, like this, with distinct eigenvalues. So this is the kind of thing I care about, and it turns out for our purposes, the values of the eigenvalues will not matter. The actual eigenvalues will not matter. All that matters is distinct. So this is the generic case for this particular M, right? But I'm more interested in the flag model. So we're looking at all like this, right? I don't need 0. And now the only non-trivial condition, right? This condition is always meaningless. It just says if I apply S to C3, I get stay inside C3. This condition is non-restrictive. It just says SV2 lives in C3. Of course it does. So there's only one condition here that matters. That condition, right? So I want to look at all such flags like this. Right, and let's look at some kind of map. Let's map to P2. We're going to take a flag like this and map it to the first space. So let's try and understand this projection. All right, so let's say given V1, right, so this is just a one-dimensional subspace of C3. If V1 is not an eigenspace, for S, right, well then V2 has no choice, because V2 contains V1 and SV1. If V1 is not an eigenspace, then V1 and SV1 are independent. They span V2. Then pi inverse of V1 is just a point. It's V1 contained in V1 plus SV1, right? I should put this 0 in C3 here, but the point is it's just a point, all right? So this thing away from the eigenspaces just looks like P2, right? On the other hand, if V1 is an eigenspace, right, which just means we know what the eigenspaces are. V1 is spanned by one of these standard basis vectors, right? Those are the only eigenspaces, right? Then, well, pi inverse of V1, right, just looks like all flags, 0 less than V1, less than X, less than C3. X can be anything, because now SV1 is just V1. And therefore, right, if I have some X that contains V1, it also contains SV1, right? This is over all X's, and this looks like P1, sorry. Right, because what am I doing? I'm picking a 2 space that contains V1, any one of them. That's the same as picking a 1 space in the quotient of C3 by V1. So this is basically like picking a 1 space from 2-dimensional space that looks like P1. So our picture looks like this. Here's P2, right? And basically I have P2, except at 3 points, I have a P1 attached. It looks like that. Right? And from this, I can read off, say, the Betti numbers. The 0th Betti number, this is connected, is 1, right? The second Betti number is 4. There's no first Betti number. the Betti numbers of P2, right, are B0, B2, and B4 are 1, and everything else is 0. So there's one cycle, if you like, right, coming from P2, and then we have these 3 1 spheres here. So we get this. Right. And so this one I can analyze. I mean, you can't, you're not going to be able to do this for too long, right? They get more complicated, but this one we can analyze directly. And what I'd like you to recall is that these are the dimensions, right, of the inverse Frobenius characteristic of GM, right? The inverse Frobenius characteristic of the chromatic quasisymmetric function for GM in this case, right? That's a bunch of representations of Sn, and in fact, we had a trivial, and a trivial plus a natural here, and the natural has dimension 3, right? So this is the idea. This is what we're going to discuss for the rest of the lecture, is that this nice phenomenon holds not only at the vector space level, but at the representation level once we figure out how to get a representation on the cohomology, right? So what we've learned is the dimensions of the cohomology groups here are nothing but the dimensions of the representations of Sn that arise from the inverse Frobenius characteristic of the chromatic quasisymmetric function for this particular M. And again, S is just generic. As long as S is regular semi-simple, it doesn't matter what S is.
John,
Go ahead, Jim.
is it? It's Bruce actually, but that's okay.
Oh, sorry, Bruce.
Not a problem. It's hard to know people by just their voice. These are the Eulerian numbers in a row of the. Is that an accident or is this?
That's definitely not an accident. And,
Okay.
and let me go right here. Right, this is a special case of this one. This is the toric variety associated to the usual the fan associated with the root system, and then work of Procesi or Stanley or Stembridge or Dolgochev and Lonzo, whoever you prefer, says that the Betty numbers are in fact the Eulerian numbers.
Yeah. Okay. Got it. Thanks.
Thanks. That's a very illuminating question. Okay. So now we have to get to work, right? Because let me remark here, this variety admits an action of S3. You can kind of see it, right? It's just permuting these 3 points, right? And you think, right, if you just think how this, right, you have P2 and these are associated to the standard basis vectors, and S3 is going to act. And so you have some action. In general, it's not the varieties that are going to admit an action of Sn, but through work of Goreski, Kotwitz, McPherson, and then Tomachko, right? One can define a representation on the cohomology of these varieties, even though probably it's not arising from an action of Sn. I mean, I don't know that anybody has disproved that it arises from an action of Sn in general, but I don't think anybody who thinks about this believes that there is an action of Sn on the variety. So the action is going to be on cohomology, right? And the Frobenius characteristic, it's going to turn out it's not going to be the chromatic quasisymmetric function. It's going to be the chromatic quasisymmetric function with the involution that exchanges H's and E's applied, right? So let me show you how to construct that, at least as best I can. All right. So the first, I want to just mention a theorem. And so this successively stronger versions of this theorem, the theorem we want appears in Damari and Shaman, but there are many generalizations, and I just would like to mention Juliana and Martha, who, right? These all have to do with, well, the work in these two papers has to do, or at least here, is some kind of Morse theory for algebraic varieties, the theory of Bialnicki-Birla. Right here, this involves affine pavings, the work of Tomachko and of Prekop, right? And the key point is that HK of SM is 0 if K is odd, and S is, let's just say, regular, right? That means that each Jordan block has a different eigenvalue. And so let's assume from now on, or at least assume for now, S is in fact generic. This is what we're going to care about. The theorems of Tomachko and Prekop apply in much more general situation. This is still true. So the cohomology is concentrated in even dimensions like it was here. Okay. So now, in fact, so we can assume S is diagonal, just for convenience sake, by what I said, right? That's completely harmless. And then we can look at the centralizer under conjugation, right? So we look at all non-singular matrices right here, and what commutes with S? S is regular semi-simple, just this torus here. Right? That's the centralizer of S. In general, a regular element is one whose centralizer has smallest possible dimension, and this is the smallest possible dimension. Right? And now what I want to assert is that T acts now, this M now is arbitrary. We're not in the toric variety case. So, but this variety, its dimension will be too big. It will have larger variety, larger dimension than T typically. And so it can't be a toric variety with respect to this action, but this action is still nice. So what do I mean? I want to use the flag model, I think. Maybe not. Yeah, I want to use the flag model, right? So what do I want to say? So let's say, so I have some SVJ, right? This is the condition for a flag to be in my Hessenberg variety, right? This implies, now instead I want to apply, right, S to TVJ. I want to translate my flag V bullet by T, but T commutes with S, right? And therefore it's contained in TV M sub J, right? Because, well, this, right, is contained in here. And so when I translate, I maintain containment. And so what this means is if V bullet, right, then TV bullet is also in there. Right, so this variety admits a torus action, and this torus action is nice. Right, what does it mean? Nice, right? The action T. This is equivariantly formal. Right, so I don't want to tell you what that is. Some spectral sequence converges. But the point is we're going to get a very nice, this is a very nice condition. The reason the reason it's equivariantly formal, whatever it means, is in fact that the cohomology, it's a nice, smooth projective variety whose cohomology is concentrated in even degrees, and that's more than enough, right? So what does it mean? It basically means, or what it implies, I guess, is that you can determine the cohomology of the variety just by looking at some kind of complex one skeleton, which is the so-called moment graph. Right. So this moment graph, along with this GKM theory, is going to allow one to get, usually cohomology, you get a presentation, right? You get generators and relations. That's how topologists often look at cohomology. This GKM theory allows you to get a representation, you get an embedding of the cohomology ring in a direct product of some polynomial rings. Okay, so how does this look? V of M, these are the vertices. And these are in correspondence with the T fixed points in our variety. Okay, now this variety sits inside the flag variety, right? And so we want to know which flags are fixed by the entire diagonal torus. Here's T here. right? So when is a flag fixed by the entire diagonal torus? When each of the subspaces in the flag is fixed by the entire diagonal torus. But now if you just stare at that for a minute, you realize that this just has to be one of the permutation flags, right? So this is in bijection with Sn, right? So the idea is, right, let's say given W in Sn, then V bullet of W is 0 less than the span of EW of 1, less than the span of EW of 1, EW of 2, and so on. All right. These are the only fixed flags, and every one of these flags lies in the Hessenberg variety. I mean, a priori, it's just in the flag variety. But since S lives in this torus, right, every one of these spaces is S invariant. And therefore, right, S does nothing, right? So if Vj is contained in Vmj, SVj is Vj. So these are all the T fixed flags, and every one of them lives in the Hessenberg variety. So those are going to be the vertices, and E of M, this is the edges. These are going to be in one-to-one correspondence with one-dimensional orbits. T orbits bounded by two fixed points. So the picture you might have in your head is T is acting on a punctured complex plane, right? Just by some multiplication according to which element of T you've chosen. And bounding this complex plane, this punctured complex plane, are a point at the puncture and a point at infinity, which are giving you a sphere, right? And so I should say these edges are labeled. The stabilizer, right, of a point in a one-dimensional orbit, right, is a codimension 1 torus. Right, whose Lie algebra is the kernel, right? It's a codimension 1 Lie algebra. The Lie algebra of the torus is just a vector space of the same dimension, right? A codimension 1 torus, its Lie algebra will be a subspace of codimension 1, which is nothing but the kernel of some linear form. L, right? And then we just label this edge with L, right? The linear form that tells us what's the Lie algebra of a point stabilizer, okay? And since this group is abelian, the stabilizer of one point stabilizes every point. Okay, so this is probably a lot of noise if you haven't seen it before, so let me show you some example, right? With M is 2, 3, 3 as above, right? And S is just this diagonal matrix. Again, these 1s, 2s, and 3s don't matter. So what I asserted, right, is that the vertices of this graph, right, this is 0 less than E1, less than E1, E2, and so on. And now I think the way I label these vertices and draw the graph seems to be somewhat idiosyncratic, because I like to multiply permutations from left to right, unlike certain people I know. Here's the graph, right? And this here right? And now I want to tell you about this edge, right? So let's look at the orbit of, I don't know, E1 plus E2. So I keep the two space the same, but this thing is not an eigenvector. right? It's going to get mapped to E1 plus twice E2, right, by S. And in general, right, if I take some torus element and apply it to this E1 plus E2, right, this is going to be the span of AE1 plus BE2, right? And here A, B are not zero, right? So this orbit consists of all things, right? First of all, this space lives inside here, so I get another flag that's in the Hessenberg variety, right? So this is a one-dimensional orbit, right? And its stabilizer consists of all matrices that look like this. And now I have to be careful, right? And let me just mention this without wasting too much time. I'm working in GL. We really should be working in SL, right? Because the torus in GL is not acting faithfully. The scalar matrices do nothing. So really here, B is A to the minus 2. In any case, right, this is the stabilizer, and its Lie algebra is just the set of all vectors, right? This is a torus, A and B are not zero, right? It's just a set of all vectors that look like this. So it's the, I'll call these variables T, right? It's the kernel of the linear form T1 minus T2. This A minus A is zero, right? And it turns out, I don't want to do any more, that you can do this everywhere. And in fact, we can read everything off combinatorially, right? This 233, right? How do I want to say this? We are allowed to exchange, right? Either things, these edges, what kind of edges are going to arise for this Hessenberg vector? We're allowed to exchange the first two entries or the last two entries. In other words, we get the two adjacent transpositions, right, on entries, right? What are these labels? Those are telling us which numbers we're exchanging, right? So there's two actions of SN on itself, either by permuting entries or by permuting positions, right? And we kind of see both actions. The presence of an edge is telling us that we can permute, right, the first two entries or the last two entries. The labels are telling us which numbers we can permute at either place. Okay, so this is the setup, and now I want to tell you, right?
So John,
Go ahead.
you're just getting weak order here, right? I mean, that's the exact same setup.
It's the same.
This is the weak order on S3.
Yes. Again, we get the permutahedron. This is the one skeleton of the permutahedron.
Gotcha.
And again, that's because of this vector, right? If I take 333, I get the other three edges that are missing from the Bruchau graph, right? If you get the whole flag variety, you see the whole Bruchau graph,
Gotcha.
right? When you take this permutahedral variety, you see the one skeleton of the permutahedron. And again, that's just because we took like, 2, 3 up to NN. Like
Exactly. That. Okay,
yes,
good.
That's exactly right. Right. In general, you see some subgraph of the comparability graph for the Bruchau order where you were allowed only certain transpositions. Right. Okay. All right. So what can you do with this? Right. I have to tell you what good this is. The point is that this allows us to determine the cohomology ring of this variety as a subring of a direct product of polynomial rings, one polynomial ring for each vertex. In other words, I'm going to assign a polynomial to each vertex in the variables T1 through Tn, right? But there is going to be a condition. Namely, the condition is going to be the difference of the polynomial assigned here and the polynomial assigned here must be divisible by this. All right. And this will be the so-called equivariant cohomology ring. So the GKM theory says, so if you don't know what equivariant cohomology is, don't worry at all. right? Like I said, it's a representation. So it's a set of all functions. In other words, I'm going to assign a polynomial with the property that if, say, I have this, then L divides f of A minus f of B. Okay. So I'd just like to show you some examples, right? So this is equivariant cohomology ring. That's a much bigger ring. The cohomology ring is smaller. I'll tell you about that in a minute, but let me first just show you some picture, right? So this was T1 minus T2, right? T1 minus T3. These are my edge labels. Right, and now I'm going to assign some polynomials. In fact, assign T1 minus T2 here, T3 minus T2 here. I don't know, T2 minus T3 here. Right, T1 minus T3 here. Right, and 0 here and 0 here. So now I just check, right? This is T1 minus T2. Sorry about my sloppy handwriting. And I just take the difference. It's divisible, right? Here, T3 minus T2 minus T1 minus T2 is nothing but T3 minus T1. It's divisible, 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 divisible. This actually lives in H2 of our Hessenberg variety. The degree of each Ti is 2. So linear polynomials will correspond to elements of H2, quadratics to H4, and so on. Okay. All right. So this is how it looks, and this is the GKM theory. It gives you a whole lot. And now I want to observe that this, right? I don't care that it's equivariant cohomology. It's just some ring. With the multiplication and addition are location-wise, as usual. Right, so it's a subring of the direct product, in this case of 6 polynomial rings, right? And so this, right, is a module for the ring itself, right? I can just take one of these things and take a polynomial in here and multiply that polynomial everywhere, right? So it's a module, and in fact, H star, right, turns out to be the equivariant cohomology mod, well, the ideal of constant free polynomials applied to the equivariant cohomology. So I can also think of this thing as living, right, in the ordinary cohomology. In the ordinary cohomology, any assignment in which every polynomial is divisible by a given constant free polynomial counts for 0, right? So you lose a lot of stuff, right? In the equivariant cohomology, I could just pick any polynomial f I want and assign f everywhere. That's completely legal, and that counts. But in the quotient, that doesn't count, right? Or at least if f is constant free, it doesn't count. Right? Okay. And if f has a constant, then you just extract the constant term. Right. So this is some nice representation. And now the thing I want to point out is that we don't know whether Sn acts on the variety or not, but it acts on this ring and also on this ring. And how is Sn going to act? Well, first of all, Sn acts on these n variables in the usual way by permuting indices. Sn also acts on this graph. I'm going to ignore the edge labels and just look at this graph, right? Sn acts by multiplication, and now there is the issue of, well, what's right multiplication and what's left multiplication, and probably I think differently than you and don't want to confuse you, right? But Sn acts on this graph by multiplication, and therefore it's going to act on the set of all functions on this graph, right, by just moving the assigned functions, right, to a new place, depending where, you move around the vertices. And now the beauty of this is that these two actions, the action on the indices and the action on the vertices combined. So I'm going to take this thing, move it somewhere, and permute its indices. And it turns out that that will preserve this divisibility condition. And this will allow an action of Sn on this entire ring, and in fact on this quotient ring, because this ideal is Sn invariant. So let me show you a picture for that. All right, I would like to show you a picture of that. All right. Let me pick this here. Let me take T1 minus T2, T3 minus T2, and put zeros everywhere else. So I hope you will believe me that this is a legal assignment. And now I want to apply the transposition 1, 2. Right, so if you remember, this is 1, 2, 3, this is 2, 1, 3, right, 2, 3, 1, at least the way I'm doing it, and so on. The transposition 1, 2 just reflects across here. Okay, so what I'm going to do, right, is take this T3 minus T2 and exchange it with this 0. So the 0 is 0. Right, but now I'm going to move this T3 minus T2 down here, except I've permuted the indices 1 and 2. Right. So this is T3 minus T1. Now I'm going to do the same here, right? I'm going to put this T1 minus T2 down here, except I will have permuted the indices 1 and 2. And these two zeros just get exchanged. And now I want to convince you that this is legal. Well, what we know, if you remember what I just slide up here if I can, unfortunately I can't, right? This difference had to be divisible by T1 minus T2, T1 minus T3, T2 minus T3, T1 minus T2, T1 minus T3, good, T2 minus T3, good. So this is the idea, right? This gives an action of Sn on both the equivariant and ordinary cohomology, right? This, what do I mean? Action on indices and action on itself by multiplication. Okay. All right, well, I see I'm running short, and so I should, now we have this action, and so I should just tell you, all right, and we'll see how much time is left, if any, after I just tell you the theorem. This is a conjecture of Michel and myself, but it's a theorem. It's a theorem of Patrick Brosnan and Tim Chow. All right. There's also a proof which is on the archive by Mathieu Guy-Paquet, which is a little more accessible. Right. Mathieu has a proof involving Hopf algebras. This proof involves some very nice combinatorics, but some very tricky algebraic geometry. Tricky is the wrong word. Advanced algebraic geometry. Right. In any case, right, the theorem is that the Frobenius characteristic so here S has to be regular semi-simple. All right, is nothing but, well, not quite the chromatic quasisymmetric function, right? So this is the thing that exchanges the elementary and, or if you prefer, it tensors with the sign character. right? However you like to say it, right? So this is the Brosnan-Chow theorem, which Michelle and I conjectured. And so, right, the graded Stanley-Stembridge conjecture now says the following. I guess C could be Q here, but the module, right, H2K, right, of Hess M, right, has a C basis permuted by Sn, in which stabilizer of each basis vector is a Young subgroup. This is the graded Stanley-Stembridge conjecture in this language, right? Because having a permutation basis with Young subgroups as stabilizers is nothing but being H positive, having H positive Frobenius characteristic, right? And so the Stanley-Stembridge conjecture, right, says that with the T grading, this thing is E positive. So when we apply omega, it should be H positive, right? The Stanley-Stembridge conjecture says this thing here is H positive, but this thing here is the Frobenius characteristic of this. And that just says that each non-trivial cohomology group has one of these permutation bases. This remains open. When we started working on this, we thought that proving this conjecture was going to be the hard part, and it was the hard part. Neither of these proofs is at all trivial. They're both long papers, right? And so it was the hard part, but this part turns out to be harder than we thought. So the idea is to try and use this GKM theory to find the permutation basis. And you can do this in any example you want. There's a Tim Chow conjectured, and now I'm going to cheat someone. I forget who proved. I apologize to somebody proved that, Sujin Cho, Jae Yun Hung, and Yun Jung Lee, sorry, proved that, that a certain basis produced by Tim is in fact a permutation basis of the desired type. There are other results of Cho Hong Lee in this direction. And there are results of Megumi Harada and Martha Prekup in this direction, but this remains open, right? So the goal was to prove, well, Stembridge immanent conjectures, or get towards proving them, or the Stanley-Stembridge conjecture through these geometric means. So to me, this is maybe the most stimulating part of the paper and a good place for me to stop. Thank you very much.
Well, thank you very much.
I have a question for you.
Go ahead.
In the last half an hour, you were talking about this toral action by the torus diagonal matrix, right?
Mm-hmm.
T. Yeah.
Yeah.
And now, is there anything meaningful that can come out even instead of this diagonal matrix if you take a tri-diagonal Hessenberg matrix?
So the trick, then you won't have a group, right? You need some group acting, right? So the set of tri-diagonal matrices doesn't form a group, right? If you take the tri-diagonal matrices, or just say the diagonal and subdiagonal matrices, right, together, they're going to generate the entire lower triangular group. And then if you have something up here, you're going to get the entire group. And in fact, the variety is not going to be invariant, right? It's not completely clear what's the largest group acting on a given variety. Certainly let me call it projective centralizer. The centralizer of the element acts on the variety. It doesn't matter what the centralizer is, this argument applies. And in fact, the so-called projective centralizer, things that conjugate S to some scalar multiple of S will act, right? Depending on the Hessenberg space, other things can act, right? But the actual automorphism group of the variety is not totally trivial to determine. And it's not clear, like, if knowing something about that action will help rather than just having the torus action, right? There is equivariant cohomology then, but it's not at all clear. I mean, there's not such a nice theory, as far as I know, for equivariant cohomology for arbitrary group actions as there is for torus actions. And I think there might be some theory when you have the product of a torus and, you know, some copies of the additive group, some nice abelian group. But as far as I know, you cannot get too much further by looking at other groups. Is that responsive sufficiently?
Thank you, John. Again.
A question, you have these really interesting modules that you get in the regular semi-simple case from GKM theory. Are there any other Hessenberg varieties where you have something like a dot action on the equivariant cohomology from a GKM graph? Or?
So this, I guess, this is tricky. So most certainly, right, like if you look at the Springer fibers, you don't have the dot action, right? You have to cook up some other SN action to get somewhere. I mean, in general, if you have some regular element, right, then there's some smaller torus acting, right? And you can then draw this graph, right? And then, I don't know, I would expect that something like, you know, parabolic subgroup of the Weil group or something will act, right? But this, I don't know any good results. It's a very good question. The best results, of course, are that you can extract the irreducibles from the Springer fibers, right? Which doesn't come from the dot action. I should remark that since we know, right, the Schur decomposition of the chromatic quasisymmetric function, we know the irreducible decomposition, right, for this action, but it's not super interesting. You don't get something, you know, really nice like you get from the Springer fiber and this other action, right? So I think the right answer is I don't know, but something interesting could happen. You might need to adjust. Right? I don't see from the GKM graph what you would get in the non-generic case.
Right. Thank you.
Sure.
John, could you go to the last page again? So I just wanted to mention that my student, Kyle Solano, has also found a permutation basis for a particular Hessenberg vector. So I just wanted to mention, add his name to the list of names.
Oh, thank you. And I'm sorry I forgot that. You told me that. So I did know that. So sorry to Kyle.
Oh, that's okay. So that's all. That's all I wanted to say.
I thought when you told me to move, I thought you were going to tell me I made a mistake.
No.
Well, I did make a mistake.
You did
but
make
not that
really
kind of
bad,
mistake.
a really bad mistake.
Yeah, that's right.
Well, I had one question. It's maybe not likely, but so you have this nice model for the monomial expansion of these chromatics. But from representation theory, it's really omega of the chromatic. Is there any expansion for the monomials of that?
So this seems to me, I'm worried that I'm going to screw up with the omega, right? It seems to me that this is, in some sense, part of the Brosnan-Chow theorem, because what they're doing is trying to understand the fixed points of a Young subgroup in this representation, right? But the fixed points of a Young subgroup are exactly, right, what's the coefficient of M lambda? That's what it's telling you, right? So I think, you know, I might be making a mistake, but if I'm not, I think the answer is yes, this is the content of the Brosnan-Chow theorem.
Okay.
But you know, you're right that sort of once you put the omega, what the colorings are telling you once you put the omega on are the coefficients of these forgotten symmetric functions, right? But what the M's are telling you in omega are exactly the fixed point spaces for Young subgroups in this action on cohomology, right? The dimensions of the fixed point subspaces. So I think some answer to this is either implicit or explicit in the work of Brosnan and Chow.
Okay. Any other questions? So there's no seminar on Tuesday because of the Alcove conference that many people want to listen to. So we'll look forward to Michelle on a week from today, on Thursday.
There's a conference on, if I have it straight, on Hessenberg varieties. Isn't that next week, or maybe I have the date wrong?
Yeah. It's
Oh,
yeah.
is that the summer school?
Yes, the summer
Yeah.
school in Montreal. So that runs all week. So
How about if we
maybe,
take next week off then?
yeah, maybe that would be good.
Yeah, because I wanted to,
yeah,
even though I'm not a grad student, I thought I would
right. So
log in and listen to some of the Hessenberg talks. So
right. So maybe
So-
I don't know if there's a talk exactly at this time, but maybe I didn't check that. I just noticed that it goes on all week.
that's
Anyone
Franco's
know?
here. Maybe he knows.
Oh, Franco, is there a talk at? I mean, we could wait till the fall.
yeah, I think we should wait just because it's
Right. It's
too much.
enough. Yeah, it's too much. Exactly.
I mean,
Okay.
I definitely would appreciate waitings. This way I can also attend. But
Right.
I guess there is no talk at exactly this hour, but it is the
Yeah,
lunch
but
break.
it's
Yeah.
lunchtime. No one wants to give up their lunch. Yeah. So great.
Thank you.
Okay.
Okay, great. So a week from Tuesday then, that's when we'll be
Right.
back.
Right.
Right.
And I
ready?
have a really tough act to follow.
You
but
do.
I'll do my best.
That's right. And you're the final leg of the relay team. That's usually got to be the best.
You know,
I
John.
thought you
may
were going
be
to say the
speaking
brains of
again.
the outfit. That would have been.
But John has given you a big lead to work with here. So,
Right. So
okay.
okay.
All right, everyone. See you a week from Tuesday.
Thank you very much.
Yeah.
Bye.
you.
Bye.
Thank you.
Bye.
Thank you.